Good afternoon, everyone. My name is Arnesh Palanisamy. I'm a second year PhD student at the Joint Unit of AgroParisTech and INRAE. My topic of my PhD thesis is thermal effects on rheology of starch granule suspension. I'm advised by Dr. Denis Flick, Marco Ramaioli, Paul Menut, and Artemio Plana-Fattori. Today, I'm going to give you a talk on transient DEM simulation of starch granule suspension undergoing thermal treatment. Without a further ado, let's move on to the outline. So we initially discussed the starch gelatinization, suspension transformation during gelatinization, and the kinetic model for individual starch granule swelling. Then we have the DEM Hertzian contacts introduction, and also the transient DEM modeling of starch swelling. Then we discussed some of the results and conclusions out of this. Also lay some future works that could arise out of the current work. So starch gelatinization is nothing but the swelling of the starch granules in presence of heat and water, and also a rupture of the granules at a later instances, releasing amylose into the continuous phase, which is water. So during this process, the suspension viscosity initially increases and later decreases when the rupture and the amylose leaching occurs. For the current work, we intend to use only chemically modified maize starch, which has less than 1% amylose, and there is no rupture and leaching of amylose into the continuous phase. Thus, we only have an increase in the viscosities. So during the path of the starch granule inside a thermal reactor, typically in an industrial setting we have a tubular PFR which is used for transforming the starch, that is gelatinizing the starch. So initially we have the suspension, starch suspension as the raw material and pumped into the reactor, and in the out and we expect and completely transformed at the outflow. So the heat is supplied through the walls of this cylindrical PFR. Initially we have the granules in an unswollen state, and the volume fractions are less than 10%. So if we can broadly divide this path of the starch granule inside this thermal PFR reactor, it can be divided into three states. Initially we have unswollen state where the volume fraction is very low and the granules are only interacting with the continuous phase, and there is no interaction of the granules and granules. In the partially swollen state, we have the volume fractions ranging from 10% to 60%. Here we have some of the granules interacting with each other, but still the fluid and granule interactions are the majority. And in the fully swollen state, where the volume fraction is very close to the 5 RCP or even greater than that, we have multiple contacts existing between the granules and its neighboring granules. So during this process of starch gelatinization, the rheological behavior, as previously mentioned, changes. So during this path of this starch suspension inside a reactor, even though we start with a parabolic profile, as the gelatinization occurs, the rheological behavior changes, which changes the fluid flow, which changes the heat transfer. So it is a highly coupled process, and the velocity field, temperature field, and the concentration fields and the product transformation gradient all change throughout the reactor length of the reactor. And one would like to have a knowledge of these parameters to be able to design better processes, better process equipment design, and also the control strategies. So now that we have established, we would like to achieve this, but to begin with, one should know how the granule diameter increases during gelatinization. So this is the first step. So to know the same, we have performed certain experiments with an optical microscope linked with a Linkham hot stage. So a dilute suspension of starch granules with water was prepared, and it was observed under the optical microscope, which was subjected to time temperature history, and images were captured at regular intervals, and these images were post processed using image plugin for developed by Francois Delange. So this results in a ferrite diameter versus versus time for individual granules. Here you can see in the left hand side some of the uh, granules which are unswollen at the beginning of the microscopic experiments, and in the second image you can see the swollen starch granules. So the typical ferrite diameter versus time data is represented in the plot in the right hand side bottom of this slide. So initially we have the diameter, almost a constant diameter di, and it at given a certain time temperature history, the granule starts to swell at a certain time, and it increases rapidly. The diameter increases rapidly and it reaches the final steady state value of df. So we can extract the time onset, the duration of swelling, and also the ratio of the final to the initial diameter. So these parameters are reported in the table 2 with mean and standard deviations given for all of them. And also in table 1 we have the time temperature histories of the cases A to E. So in literature there exists multiple efforts to characterize this gelatinization process as a kinetic phenomena. So we follow a similar approach, and we define a non-dimensionalized parameter S, which is the non-dimensionalized diameter, which is equal to dt, which is the diameter at an instant t minus the initial diameter divided by the final diameter minus the initial diameter. So in the hydration zone we have a constant ds by dt equal to 0. In the swelling zone we have a rate equation which is depicted in this slide. We also see that based on our experiments that the granules did not begin to swell at the same instant, but there is a time delay in the onset, and this time delay in onset varies between granule to granule, and this variability is higher at lower temperatures compared to at higher temperatures. The same has been mathematically casted here, and we see that it approximately follows a 1 minus exponential curve fit, the time delay in this onset. Here you have the experimental data and the curve fit for the same. We also see that the granules which started to swell at a later instant tend to swell slower compared to the granules which started to swell at an initial instant. So to capture this thing, we introduce a parameter called the difficulty of swelling, alpha, which is from a uniform distribution of 0 to 1, and it depends from granule to granule. And using these equations, we have a rate equation ds by dt equal to k into 1 minus s. So this is first order reaction where k is equals to k reference into 1 minus alpha power 0.5 into t minus t min divided by the t ref minus t min to the power square. So you have a temperature dependence of the rate constant and also the granule dependence. So using these rate equations, we were able to predict the experimental data, which you can see in this plot here. The audience are referred to our recent publication in Food Structure Journal. The link to the same is shown in this slide. for further details regarding this kinetic model as such. So we have the parameters for this kinetic model, and we use the same to couple it with the DEM. So what is DEM? DEM is a Lagrangian method which solves for Newton's equation with a predetermined time step, and there exists multiple contact models in this approach, and Hertzian contact model is one of them. Hertzian contact model states that there exists a repulsive force which is proportional to the overlap distance delta n power 3 by 2 if two spherical particles has a overlap length of delta n. So this Hertzian force takes into account the curvature of the spheres, and we have a force equations if there exists an overlap. If there is no overlap, there is no force, of course. And here E and nu, E is the Young's modulus, nu is the Poisson's ratio, and R1 and R2 are the radius of the two particles. So here our simulation domain, so for performing the starch granule swelling using DEM, we make certain assumptions, and our simulation domain here is a cube in a Cartesian coordinate system x, y and z. So we assume all the granules are spherical, as you have seen earlier from the microscopic images. All the granules are not exactly spherical but have an aspect ratio of around 1.2, but for this simulation we have assumed they are all spherical and have the same Young's modulus. We did not consider any tangential forces, or we did not solve for the angular velocities or of the spheres, so we are only considering the normal forces, and we did not consider any gravity force on the particles. Also, we are assuming the particles are non-Brownian, which is to considering the size ranges. And also, we did not consider any lubrication forces. So the lubrication forces exist because of the fluid layers in between the particles. So it's a dissipative force. We did not consider that in this present study. And also we considered a periodic boundary conditions. So what is periodic boundary conditions? So if a particle with a velocity exits a certain phase, say minus y, it re-enters through an opposite phase from the plus y direction. So we use a periodic boundary conditions for that. And here also we see the time temperature of history that we are imposing on this simulation domain, which is nothing but it starts at the 60 degrees and increases to 80 degrees within a span of 4 minutes. So here we have the results. This is the cross section at the center of our domain box, and we have the contours of the granules. So initially at time t equals 0, all the granules are in an unswollen state depicted by the plus sign, and at time t equal to 30 seconds, one of the granules have already started to swell, which is depicted by the dots. But since they did not yet start to interact with each other, the initial positions are conserved, so it's the same. But whereas in time t equal to 60 seconds, some granules have interacted, and they have caused a displacement dearrangement in the box, and the granules have rearranged, and progressively they further rearrange. So this rearrangement occurs because when the granules come in contact, there exists Hertzian interaction forces, and the granules push each other such that and move so that the system is under minimum interaction energy. So here you have some more results. In plot A, we have the time temperature history, and in plot B, we have the number of granules beginning to swell as a function of temperature, function of time. And plot C, we have the mean radius as function of time, and in plot D, we have the volume fraction granule of the granules as function of time. So initially we have a volume fraction of less than way less than 0.2, and at the end of simulation we have the volume fraction of the granules much higher than 0.6, and in the plot E we have the measure of polydispersity of the suspension. So at initial instances, there is a certain polydispersity, so, and it increases because granules some granules start to swell, so the polydispersity increases, and it later decreases because some of the granules which did not swell were adding to the difference in the between the granules which already swell, so the polydispersity is higher. But at a later instances, these unswollen granules tend to catch up with the swollen granules, and the polydispersity decreases. So we see that all the granules began to swell after 200 seconds, and the mean radius increases maximum after 100 seconds, and the volume of the granule increases 12.8 times. So as discussed, the dispersion of the population increases initially, and then it decreases before reaching a maximum value. So in this slide, we have the comparison of the interaction, the jamming parameters as a function of volume fraction and also the time. Here also we plot the interaction, the volume fractions, 5 RCP, which is calculated based on the formula proposed by Farr and Groot for this polydispersity. And we see that the interaction energy increase of our suspension increases at a higher volume fraction compared to this prediction, because the 5 RCP is for this hard sphere. So if our system were to be a very hard sphere, the interaction uh, parameters would have increased at this 5 RCP. But rather, since our system is a soft sphere suspension, this volume fractions increase at a later so this interaction parameters increase at a later volume fractions. So to conclude, we demonstrated the modeling of starch granule suspension evolution during gelatinization using DM. So the earlier developed kinetic model for individual starch granule swelling was coupled with DEM, and they're resulting in the transient DM simulation. This approach, one can get the size evolution as a function of time, and also certain interaction parameters as a function of time. From this study, we see that since granules are soft spheres, the increasing in the jamming indicators occurs at a volume fraction greater than the prediction based on the analytical solution for hard spheres. So for future work, we would experimentally like to characterize the Young's modulus and incorporate the same in the model, and also include tangential and lubrication forces and other forces as deemed necessary, and study the influence of the box size, and also perform shear flow simulations for the same system to capture the viscosity evolution of the suspension. And we like to acknowledge and thank our funding agency, the European Union Research Framework Program H2020, and MSCA Actions ITN program Mathigram, which is this PhD is a part of this ITN Mathigram. Thank you for your attention. I'm open for questions.